Welcome to this introduction to IPFS, which stands for InterPlanetary File System. IPFS is a revolutionary approach to storing and sharing files on the internet. Instead of relying on centralized servers like traditional websites do, IPFS uses a decentralized network where files are distributed across many computers around the world. This makes the web more resilient, faster, and gives users more control over their data. Think of it as a new way to organize the internet, where content is stored everywhere and nowhere at the same time. To understand why IPFS exists, let's look at the problems with today's web. First, centralized servers create single points of failure and control. When a website goes down, all the content hosted on that server becomes inaccessible. Additionally, centralized systems give too much power to a few large companies. Second, the traditional web uses location-based addressing, which means files are accessed through URLs that point to specific server locations. When servers are moved or shut down, links break and data is lost forever. This is called link rot. IPFS solves both of these problems by using decentralized, content-addressed storage, where files are identified by what they contain rather than where they are located. IPFS is built on three core concepts. First, it's a peer-to-peer network, meaning it's a distributed file system that connects all participating computers directly without needing central servers. Each computer in the network is called a node, and they work together to store and share files. Second, IPFS uses content addressing, which means files are identified by a unique fingerprint of their content, called a hash, rather than by their location. Third, IPFS provides version storage with built-in version control, allowing you to track how files change over time. Together, these features create a more robust and reliable way to store information on the internet. Let's compare how traditional web and IPFS access files. On the traditional web, files are accessed by location using URLs. For example, when you visit example.com/file.pdf, you're asking a specific server at a specific location for that file. If that server moves or the file is relocated, the link breaks. In contrast, IPFS uses content-based addressing. Files are accessed by their content hash, which looks something like qm.abc123. This hash is generated from the file's content itself. No matter where the file is stored or how many copies exist across the network, the same hash will always point to the exact same content. This makes IPFS links permanent and ensures data integrity. At the heart of IPFS are content identifiers, or CIDs. A CID is a unique cryptographic hash that acts as a fingerprint for your file. For example, a CID might look like this long string: QMXOYP, IZJW3, WKNFIJ NKLWHCNL, 72VEDX, JQKDDP1MXW06UCO. Every file added to IPFS gets its own unique CID based on its content. Here's what makes CIDs powerful. If two files have the exact same content, they will have the exact same CID, which guarantees data integrity. However, if you change even a single byte in the file, it will generate a completely different CID. This ensures that when you request a file by its CID, you always get exactly what you asked for, without any tampering or modifications. Let's walk through how IPFS works step by step. First, when you add a file to IPFS, it's split into smaller chunks, typically 256 kilobyte blocks. This chunking makes storage and transfer more efficient. Second, each chunk is cryptographically hashed, creating a unique identifier for that piece of data. Third, these chunks are distributed across the peer-to-peer network. Multiple nodes can store copies of the same chunks, making the data highly available and resistant to failure. Fourth, when someone wants to retrieve your file, they use its CID to request it from the network. IPFS finds the nearest nodes that have the chunks, retrieves them, and reassembles the original file. This distributed approach means files can be retrieved faster because they're downloaded from multiple sources simultaneously. IPFS offers several major benefits over traditional storage systems. First, it enables faster downloads. Because files can be retrieved from multiple nearby peers at the same time, download speeds are often much faster than downloading from a single distant server. Second, IPFS provides resilient storage. Files persist across multiple nodes in the network, so there's no single point of failure. Even if some nodes go offline, the content remains accessible from other nodes. Third, IPFS includes built-in security through content verification. The cryptographic hashing ensures that files cannot be tampered with, because any modification would change the CID. Fourth, IPFS reduces costs by eliminating the need for expensive centralized server infrastructure and bandwidth. Instead of paying for hosting, the storage burden is distributed across the network. IPFS transforms how we store and access data by replacing location-based addressing with content-based addressing. This creates a more resilient, efficient, and decentralized web where data is permanent, verifiable, and always accessible. By distributing files across a global network of peers, IPFS removes single points of failure and puts control back into the hands of users. As we move towards Web3, IPFS serves as a critical building block for decentralized applications, providing the storage layer that enables truly distributed systems. Whether you're building decentralized apps, preserving important data, or simply looking for a better way to share files, IPFS offers a powerful alternative to traditional centralized storage.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.